So we've got to grips with a variety of projectiles and projectile situations. In year 12, we looked at vertical projections. And in year 13, we've looked at horizontal projections and projecting at an angle. So an unknown angle or an angle that's given to us, and we've worked on that. What we want to look at now is a more generalized situation where actually we don't know any of the variables, but can we get an expression, a formula that links these variables together so that as soon as we do know the variables, we can do some substitution, we can plug in their values and generate the correct expression. So here's a generic flight path, and I've just drawn from the ground to landing on the ground. You can see that we've got the initial projection of u and the angle of elevation of alpha. I can still express the vertical and horizontal components in terms of u and alpha. So u cosine alpha and u sine alpha. So if I wanted to get an expression for the time of flight for this particle, so that's the time that it takes to get from A to B, I'm going to work with vertical components and I can set up my variables. Firstly, displacement will be 0 when it gets back to B, it'll be back on the ground. Initial velocity, u sine alpha, unknown final velocity, acceleration, negative g. We won't even use the 9.8 here, negative g, and an unknown time of t. So my expression, using s equals ut plus half at squared, substituting in these values, I'm trying to make t the subject. I want t to be the time of flight. I get an opportunity to factorize, and that lets me know either I have t equals 0, or I have this bracket equal to 0. If we set the bracket equal to 0 and just rearrange, I can isolate the t, and we get t equals u sine alpha over half g. Just making sure I don't have a fraction on the bottom, I'll multiply the top and the bottom by 2. And this is the expression we're looking for, 2u sine alpha all over g. So this is the general expression for the time of flight of a particle, and that will be the time it takes to get from point A to point B. Okay, we can also get a general expression for the time to the highest point. So this is going to be to the peak of the flight path. So we'll set up some vertical variables. We know that the vertical velocity at the highest point is 0, and then we'll fill in the rest as usual. So it's unknown displacement, u is u sine alpha, acceleration of negative g, and we'll use the variable t. So we can plug this into v equals u plus at, and we're just rearranging to isolate t to make t the subject, and we get an expression u sine alpha over g. Interestingly, I hope that you notice one of them is twice the size of the other. And if we go back to the original diagram, it actually makes sense. Let's call this peak C. The time it takes to get from A to C, it's half the time from A to B. And if we look horizontally, it's half the distance. Since velocity is constant in the horizontal direction, it's going to take half the time to travel half the distance. So this relationship you may not have noticed before, but can come in useful, that as long as the projection and the end of the projection are on the same level, usually described as being on a horizontal plane or being on the ground, then the time for the particle to reach its greatest height is going to be half of the time that it takes the particle to get to the greatest height and then back down to the horizontal plane, back down to the ground. Okay, so now let's look at the range. Remember, the range is the horizontal distance traveled by the particle. So we'll set up our horizontal variables. We're looking for the displacement. The initial velocity is going to be u cosine alpha. Final velocity is also u cosine alpha because the acceleration is 0. And t, time, is going to be t. Now this is the same t that we used for the time of flight of the projectile. So we are going to substitute that in at some point. Let's start with our expression. So the equation to use, s equals ut. And And I'll substitute an R for S for now, since the displacement is going to be the range. U and T, I'm putting in that expression, as I said. It's just to tidy this up a little bit. We get 2 U squared, and then we're going to get cosine alpha sine alpha over G. And I hope you recognize here, we have a trig expression. We have the double angle formula expression, 2 cosine alpha sine alpha, which is the double angle formula for sine 2 alpha. So we'll rewrite this as sine 2 alpha. So in the numerator, U squared sine 2 alpha, denominator G. And this is the expression for the range of the projectile. To get to this point, there was an expectation that you were familiar with the double angle formula and its 2 forms. There is an expectation that you can spot opportunities to apply some of the techniques that you've learned in pure maths over here on the applied side. And it's part of the skill set the exam board and the examiners, and even I, as your teacher, would expect you to be able to demonstrate. There's some other things that we might need to apply here. This trig expression, we could easily be asked, what's the maximum value that the range could take? Just like you do over in pure, the maximum, we need to consider the variable of the trig function, so the variability of sine 2 alpha, and we realize the maximum sine 2 alpha can take is 1. So then the maximum value of the range is U squared over G, with sine 2 alpha being 1. Similarly, we could be asked about the minimum would occur when alpha was -1, that the range can take all values in between negative U squared over G and U squared over G, positive. Be on the lookout for opportunities to apply techniques that you know and you've seen elsewhere in maths. Okay, so the last bit that I want to look at when it comes to generalizing and using projection motion formulae is trajectory. So trajectory is when we actually produce a Cartesian equation for the position that a particle might take at any point during its flight. Here is actually a show that question, but we should be able to produce it without it being part of a show that question anyway. So we're going to start with our vertical variables. I'm going to call the vertical displacement y, and the others as you would suspect. So by doing some substitution, I get an expression for y in terms of t. We'll move over to the horizontal variables, and I'm going to call the horizontal displacement x. This is how the Cartesian coordinate system works, the x and y values. So I'm going to get an expression for x in terms of t. We'll use the formula s equals ut. And here I have 2 expressions, one for y, one for x, both in terms of t. This hopefully reminds you of parametric equations. If I rearrange dx to make t the subject, I can then substitute that into the expression or equation for y. So let's go ahead and do that. Here I get u sine alpha multiplied by x over u cosine alpha, subtract half g, x squared over u squared, cosine squared alpha. Just be really careful with this. We want to do some tidying up now so we can see exactly what's happening. U's will cancel, sine over cosine generates tan, and we've got a coefficient of x. I'm going to take all of these constant variables, well, I'll take the x squared as well, and I was going to write them separately to the trig expression, 1 over cosine squared. I hope we're all happy that that is going to be sec. Right, rearranging a little bit more, trying to get into the form I was asked to in the question. And we get sec squared alpha, and one more step to hit the show that expression. We're going to change or substitute sec squared for 1 plus tan squared. All right, and this is the expression we were looking for. Even without the show that part of the question, we would have tried to move towards having the same trig function within the expression anyway. There could be some problems where we might need to solve, and solving is so much easier when we have the same trig function throughout the question. So a quadratic involving tan is where we're going to go with this. I want to make it clear to you that you may be expected to anticipate. You may be expected to take those intuitive steps yourself. So once again, you're pulling in some skills from pure and you're using them in applied. I'd like to recommend that you don't compartmentize these two aspects of maths too much in your head. You can and will be expected to use all the skills you use in pure within this applied module. Okay, so let's just move on to a situation where we're actually given values for these variables. So the initial velocity is 28 and the position horizontally is 32 while vertically is 8. We'll just go ahead and substitute these values into the expression that we had, so the one that we just generated. And we're going to try and simplify it from here. So this whole coefficient of the bracket simplifies away to 6.4. And I'll expand at the same time. So subtract 6.4 tan squared alpha. And like I was saying earlier, I hope you can see right here, we just have a quadratic in terms of tan alpha. So go ahead and solve the quadratic. I really want you to just put this into the equation solver rather than the equation itself. So just use the equation solver function on your calculator. If you don't have that calculator, you do have to spend a couple more minutes doing it the long way around. Either way, we get solutions. Tan alpha equals 1/2 and tan alpha equals 9/2. And these lead to angles alpha equals 27 degrees or alpha equals 77 degrees. Okay, so the two possible angles of projection that would make us go through the coordinates 32, 8 are 27 degrees and 77 degrees. If you're finding it hard to visualize how comes two different angles can get us to go through that same coordinate point, it's because I either have a very steep projection or a very shallow projection. The shallow one, I go through that point on the way up, and the steep one, I go through that point on the way down. Okay, so there's a variety of situations where we're working very generally to get expressions for different components and aspects of a projectile in motion. Just to summarize, here are the expressions you might be asked to generate. I in no way expect for you to learn these. The examiner and the exam more want you to be familiar with them and to be comfortable in producing them right from scratch in the ways that I've demonstrated.